Professor, this is my project for this subject, real-time tracking using deep association metric. Let's see what is the objective of this model. The object number one is real-time multi-person multi-object tracking, and the object number two is that we integrate appearance information to improve the occlusion problem. So we'll first we'll see what algorithms we use for multiple object tracking, and later we'll see which algorithm used for occlusion, and finally we did the experiment with my lab mate. So I'll show you how the model was performing. Yeah, these are the contents of the table, the objective, the problem statement, the data processing which we use it for the mm, bounding box generation, and the network structure of our model, and finally the experiments we did, and what are the performance of on different platforms. That is one of our objective. And finally conclusions. Yeah, if you see the problem statements, we have implemented real-time person tracking with deep sort association metric learning. For the bounding box generation, we use the cafe pre-trained CNN model. This is for just generating the bounding boxes. Later, we have used the concepts of Kalman filter, Mahalanobis filter, and cosine distance metric to solve the occlusion. Finally, we use the intersection over union to provide the ID. And finally, yeah, for let's see the data processing. We for this we use the pre-trained CNN model, which is trained on COCO data set. So this provides two contributions to a project. Contribution number one is tracking the object, and contribution number two is low computational person re-ID. These two contributions provides by the Cafe model. Yeah, let's see about our neural network model. So what we did is we created one video. This video we given frame samples to five frames, five. So uh, let's see from Kalman filter, then Mahalanobis, then cosine similarity, final intersection. Let's see from Kalman filter how it's going the video. So we sample into five frames. So after generating the bounding box from this cafe data set, we'll send it to the Kalman filter. So from getting inputs of these five frames, the next two frame is will next two frames x and y coordinates will be generated by the Kalman filter. But in order to make sure the x and y coordinates provided by the Kalman filter are better, or like maybe accurate or predicted output are accurate, we are using the Mahalanobis filter distance metric. So from here we are validating the x and y coordinates generated by the Kalman filter. So if the x and y coordinates predictions generated by the Kalman filter are more than 0.95, like 95%, then we are accepting as like uh, better prediction. Then only we'll uh, take the input of the frame. Yeah, the you can see the mathematic space at I, and DJ. DJ are the predicted frames, and ith frame is the current frame. So the next two frame, the predicted frame prediction is more than 0.95, then only will take accept it. Yeah. Now we have generated the boundary boxes and multiple tracking are both being done as assume. I will show that in the results whether they are being done or not. As assume that thing is happening. Now we have to check the similarity, I mean occlusion. So when the ID one is coming over here and ID two is over here, when these two get overlap each other, maybe ID one front and ID two behind, ID2 front and ID1 behind. So now we have to, the bounding box should not be swapped or missed. So for that now using the cosine similarity. The cosine similarity is to give an ID to the tracked object. Here we given the like whenever there is a scenario of occlusion, uh, we are using the cosine similarity, and we given the buffer time of 600 seconds. So ID1 is coming over here and ID2 is here. So ID2 is in front and ID1 is behind. But now the model can predict only ID2 but could not see the ID1. So in order to issue to overcome the issue of occlusion, we given 600 seconds as buffer time. So until 600 seconds, it will the ID1 will be kept in buffer. So unless how to say, yeah, whenever a tracked object is not found for a certain time, tracked object and the past tracked object is compared. If they both have similarity more than 95%, then his ID is given to the overlapped object. Intersection or union. Finally, we gated cost matrix to intersection or union by combining the results of Mahalanobis distance metric and cosine similarity metric. In this cost metric is calculated for the tracked object and detected object. The tracked object is the ID1 which went to the backside, and the detected object is the ID2 which come to the front. By this it can compare both ID1 and 2. Yeah, this is a simple like a flow chart designed to explain you clearly. Yeah, you can see here. Mm, second. Yeah, you can see here the bounding box. We are using the cafe model to generate the bounding boxes for multiple objects, whether 1%, 2% coming for generating bounding box using this cafe model. Then we send to the Kalman filter. The Kalman filter, it will predict the next frame positions of and y. So we'll check whether the predictions are, if the prediction is greater than 0.94. So it's given like around 943 something, like 95%, by using Mahalanobis filter. If the prediction is over the 94%, then only we'll consider it as the true prediction. Then the situation of occlusion. When occlusion is occurs, we given the buffer time is, you can see the given buffer time is 600 seconds. So it will keep on comparing the similarities between the tracking object and the detected object. So the ID1, which is being tracked during this all the process from the bounding box, Kalman filter, and validation everywhere, is being tracked up to here. And the new one, the detected object. So when these two are overlapped here, in this overlap here, the cosine similarity will find out the similarities between the the tracked object and detected object. So for that, we given like 600 seconds. Until 600 seconds, the ID1 can be behind the ID2. Until this time, within this time, if the ID can be shown to the frame, it can able to find out the similarities. Then finally, we use the intersection over union to give the IDs for each tracked object and detected object. So I'll show you now the experiment we made. So whatever it is, the ID1 is coming is being tracked. It will shows the ID1 only. It will instantly detects ID2, then it will be states ID2 only. If the crossover or overlap one to behind, so still the IDs are not been IDs haven't been changed. now you can see here, you can see the experiment. Now we have made two changes to the, sorry, 1 second. Yeah. So we have conducted experiments by changing various hyperparameters. They include the max age, number of misses before a track is deleted, and any number of frames that a track remains in initialization phase. So we validate these parameters in different platforms because testing our one of the motto is to use like low embedded systems. So we performed in different platforms to show the performances. You can see here. On GPU, the performance like we achieve at 30 to 35 frames per second. You see on low embedded computing systems, it is from 18 to 25, and it is the model run on GPU with RTS 2060. It is like some 5 to 45 frames per second. Yeah, and you can see here, this is just like up to the Kalman filter result. The my mate, the bounding box and ID generated for him. And you can see here, me and my roommate, both we were walking each other. You can see my ID is number one and my ID is number two. When we are overlap each other also, the IDs are like one and two. When we crossed each other and trying to overlap again, still the IDs like to my mate is two and for me is one. So in this way, uh, it will be like whenever the occlusion appears also, the model will be remains same. The ID is generated for the tracked object will be remains same. Yeah. So and also like this is not only done by me but along with my friends, but actually they are not in the class, so giving credits to them also, and these are the references for this. Thank you, Professor.